Hi, I'm Harshita. So today I am going to be presenting my GPU Specialization Capstone Project, GPU Accelerated Image Filter Pipeline. So the goal of this project was to apply multiple image filters, the grayscale, sepia, blur, edge reduction. So using the CUDA kernels to leverage the massive parallel processing power of an NVIDIA GPU. I chose this project because I really enjoyed the image processing assignments earlier from the course and wanted to explore more filters while learning CUDA parallel programming. So this project combines the computer vision with the high performance GPU computing, and it's something you can actually see the results of visually. We'll be processing a space image through all four filters, and you will see how the GPU can process nearly a million pixels simultaneously in just milliseconds. So before we dive into the code, let's first understand few concepts. First would be the CUDA. So CUDA stands for Compute Unified Device Architecture. It's NVIDIA's parallel computing platform that allows us to use the GPU for general purpose computing beyond just graphics. So we can think of it like the CPU has a few powerful cores, typically like 4 to 16, and is optimized for sequential processing. A GPU, on the other hand, has thousands of smaller cores designed for parallel processing. So here are like some terminologies. Host refers to the CPU and its memory. Device refers to the GPU and its memory. Kernel is the same function that runs in the GPU, so you can take a look of these. So the execution model follows this hierarchy, which is given here. So grid, blocks, threads, and then each thread processes one pixel. So for an image with 9,45,920 pixels, we launch enough threads to process every pixel simultaneously. Now, let me explain the four filters we are going to be implementing. First will be the grayscale. So the grayscale filter uses the luminosity method, which is the most accurate and commonly used approach. So here is the like gray equals 0.299 times red plus 0.587 times green plus 0.114 times blue. So these weights match human perception. We are more sensitive to green and least sensitive to blue. And next will be the sepia. So sepia creates a warm vintage look by applying weighted sums to each RGB channel. So like these are the formulas. Red new equals 0.393 times red plus 0.969 times green plus 0.189 times blue. And green u equals 0.349 times red plus 0.686 times green plus 0.168 times blue. And then here's the blue nu. So we clamp the values to stay between 0 and 255 to prevent integer overflow. Next will be the blur. So the average blur filter replaces each pixel with the average of itself and its 8 neighbors. So this is called as convolution operation with a kernel of ones. So the output for each pixel is the sum of the 3 to 3 neighborhood divided by 9. So each pixel don't have all 8 neighbors, so we keep them unchanged to avoid going out of bounds. And the final would be the edge reduction, so which is also known as Sobel. So the Sobel operator detects edges by calculating gradients. So here the Gx detects horizontal edges, calculated as the difference between the right and the left columns. Gy detects the vertical edges, calculated as the difference between the bottom and the top rows. The magnitude is the square root of Gx squared plus Gy squared. A large magnitude means a stronger edge. So now let me walk you through the actual CUDA kernels, which is like main of the project. So here are the grayscale kernel. Let me explain each part. The global keyword tells the compiler this function runs on the GPU but is called from the CPU. Block idx.x is the index of the block within the grid. Block dim.x is the number of threads in each block. Thread idx.x is the index of the thread within its block. Idx is the global thread ID, calculated as block idx.x times block dim.x times plus thread idx.x. So this this statement, if statement, this check prevents threads from accessing memory out of bounds. Inside each thread computes the grayscale value for exactly one pixel using the luminosity formula. Next would be the sepia. So the sepia kernel follows a similar pattern. Each thread reads the red, green, blue values for its pixels, the sepia transformation formulas, and writes the results back. Notice here like the clamping logic in this statement. So this prevents values from exceeding 255 and causing integer overflow, which would create weird artifacts. Next will be the blur kernel. So the blur kernel is more complex. Each thread calculates its row and column using the division and modulo operations. So inside the if statement, we check if the pixel is not on the edge of the image. Edge pixels don't have like all 8 neighbors, so we keep them unchanged. For the interior pixels, we use nested loops to sum the 3 into 3 neighborhood and then divide them by 9 to get the average. And the final one would be the edge reduction. The edge reduction kernel uses the Sobel operator, which we discussed earlier. So we calculate Gx using the horizontal Sobel kernel and Gy using the vertical Sobel kernel. The magnitude of this is calculated using the Pythagorean theorem. We clamp values to 255 to ensure we get a valid grayscale image. Now let me explain how we launch these kernels from Python. So first, we allocate memory on the GPU using this function. We need to allocate memory for each output channel and for the output as well. And then we copy data from the CPU to the GPU using this function that's like host to device. We compile the kernel and launch it with the appropriate grid and block sizes. The grid size calculation has here. So this ensures we have enough blocks to cover all the pixels. This is a common ceiling division pattern in CUDA programming. Next is like the kernel launch command, which kind of looks complex, but let me break it down. So the first arguments are the GPU pointers. Block specifies the number of threads per block. Grid specifies the number of blocks in the grid. Finally, we copy the results back from the GPU to the CPU using this function that's like device to the host. And then we free the GPU memory using this dot free function to prevent memory leaks. So the key thing here to understand is that GPU memory must be manually managed. So unlike Python, which has garbage collection for the CPU memory, GPU memory must be explicitly freed. So if you forget to free memory, you'll eventually run out and your program will crash. So that's an important thing to emphasize. And next would be, let me show you the output for each filter. So first we load the image using OpenCV. One important thing to note here is that OpenCV uses BGR format and not RGB. So that's like blue, green, red instead of red, green, blue. So we need to be careful about the channel order when extracting colors. And so here is the grayscale result. The grayscale filter applied in about 5 milliseconds on the GPU. Each of the 9,45,920 pixels was processed in parallel. So this could be the classic black and white conversion using the luminosity method. The sepia filter was the fastest at about 2.8 milliseconds. So this is, as we discussed earlier, a warm, a vintage look. So this is popular in photography and it creates kind of nostalgia effect. So the next would be the blur. So the blur filter took about 7 milliseconds. This requires more computation because each thread accesses 9 pixels instead of just 1. One thing that might confuse you, or it confused me. So like at first glance, grayscale and blur could look similar. The difference is that the blur perceives color information. It just averages like nearby pixels. Grayscale removes the color entirely. So the final one would be the edge reduction. So it took about 8 milliseconds and produces the most like clear, dramatic visual result. The Sobel operator highlights boundaries and edges in the image. So you can see here clearly. And so now let me show you how I measured performance and the results. So I measured performance using Python's time.time function, so which would give us high precision time in seconds. I measured both CPU and GPU implementation for comparison. Here are the results. So I've given here the gray scale filter was about 3 times faster on the GPU, taking about 5 milliseconds versus 15 milliseconds on the CPU. The sepia filter was about 4 times faster, taking about 3 milliseconds versus 12 milliseconds on the CPU. The blur filter was about 6 times faster, and so on. So basically, the GPU is consistently faster for like 3 main reasons. First would be the parallel execution. All pixels are processed simultaneously instead of sequentially. And second would be the memory bandwidth. So the GPU has much higher memory bandwidth than the CPU. And third would be the thread count, which is this much, like 9,45,920 pixels divided by 256 threads per block gives us about 700 blocks all running in parallel. This so the speed up is kind of more dramatic for the filters that require more computation, like the edge and blur reduction, because the parallel advantage becomes even more significant. Let me share the 2 challenges I faced during the project. First would be the memory management. So I had to manually free GPU memory using .free function after each operation. Without this, Python would keep allocating memory on the GPU, leading to more exhaustion and crashes. Second challenge is the blur and the grayscale results, which looked similar, especially with certain images. I had to examine the actual pixel values to verify that the blur was actually working correctly. So we've come to the end. Let me summarize the key points quickly. So CUDA is NVIDIA's parallel computing platform for using the GPU. A kernel is a function that runs on the GPU. A thread is one execution unit. In our case, it processes pixels, 1 pixel. A block is a group of threads that can share memory. A grid is a group of blocks that covers the entire workload. We have the host, which is CPU and its memory, and the device, which is GPU and its memory. Memory transfers go HTOD, which is host to device, and the DTOH, which is device to host. And parallelism means thousands of threads running simultaneously. Basically, this project gave me hands-on experience with CUDA, kernel development, GPU memory management, parallel processing patterns like the thread per pixel model, and the performance optimization, configuring the blocks and grid sizes for the optimal performance. And finally, the most important lesson I've learned is like, don't assume visual similarity means the same result. So always you can verify the data. So that's it. Thank you.